In this video, we're looking at properties of the cross product. So last time we saw that when I do I times j, I get nice k, just normally. If I do j times I actually get minus k. So we talked about how order matters. Essentially, if you look at v cross w, that is negative if you did it the other way around. So just be very, very careful when you're timesing. You can't just like swap the order in algebra stuff. Okay, so we use something called the right hand rule to figure out what way it goes. Basically, you put like your pointer finger out to the first vector, your middle finger to the second vector, and then whatever way your thumb goes is the correct direction for the cross product. So if we look at the vector I, that's going to go out here. And then the vector j goes out there. Now, I'm horrible at using the right hand rule, mainly because I'm like left-handed. You can imagine your pointer finger being the I vector, and you can imagine your middle finger being the j vector, and then your thumb would have to be the k vector. It has to point up, and then there's your, I don't know, there's your hand. You'd have to put your hand basically upside down for the next one. So if you tried to do j times I, so there's I still and there's j still, but you have to sort of put your point. I encourage you to actually like get your hand and try this because my drawings aren't fantastic, but you've got your pointy finger there, and if you want to put your middle finger there, pointy, middle, then basically you're forced to put your thumb downwards. I encourage you to actually try that if you don't believe me, but that's the only way you can sort of make that happen, unless you have very bendy thumbs. And so the result is that the cross product points downwards. Now, it's pretty rare that we actually have to use the right hand rule in something like spec maths, because you just calculate the cross product and see which direction it points. But I know that the physics people tend to like it a lot. Now, we have this other thing for finding angles. It's pretty similar to another formula for the dot product. A dot B is mod A mod B cos theta. So you can see sort of the parallels between those two. Now, let's calculate some angles of the cross product. So first of all, we need to prove that A is parallel to B. Now, there's two ways to do this. There's sort of the easy way and the hard way. The hard way uses the cross product. The easy way is how we've been doing it up till now. So basically notice that B is 2 lots of A, right? Because you would have to times by 2, 0 times 2 is 0 as well, and 2 times 2 is 4. Since they're multiples of each other, therefore B and A are parallel. Done. Now I should show you this. Like the hard way is more useful in like proofs and stuff sometimes, but let's see how we go. Those vectors should all be bold as well. So if we calculate the cross product, A cross with B, you've got I, J, and K. You've got 102 and 204. And basically, if you get 0, then the vectors are parallel. And so we'll see if that happens. So we're going to get I times the first determinant, take j times the second determinant, plus k times the third determinant. Remember, when you do this process, for example, to get the k determinant, you lop off all the ones underneath k, and you just take the other determinant that's remaining. Cool. So that gives you I lots of 0, take 0. Take j. Now, the way I got 0 times 0, 0 times 4, and 2 times 0. K would be 1 times 4 is 4, 2 times 2 is 4. So that's going to be k lots of 4 take 4. Plus k lots of 0 take 0. And what do you know? You get 0i plus 0j plus 0k. So the vector itself is 0, 0, 0. Now, you might be wondering like, okay, that's a bit weird. Why don't we get a vector for the cross product? And I guess the easiest way to explain it is if you have two vectors v and w which are parallel, then the two vectors that you started with are going to look like this. They're both going to point in the same direction. One will just could be longer or shorter than the other one. So imagine this in 3D land. You can put a vector which is at right angle, which could be a result of V cross W, but you've actually got like a whole circle in 3D that goes around it. So like if that was V and W, you can imagine like in 3D, it could be any of those vectors which sort of go around both V and W that are perpendicular. So there's actually, it's not that we can't find a vector which is perpendicular to both the starting vectors. It's that there are infinitely many of those vectors. So that is the issue. Okay. Find the angle between A and C using the cross product. So 102 and 32 minus 1. C is 32 minus 1. Now, I'm a little bit cheeky when I calculate the cross product sometimes. I don't bother writing it out in a big determinant most of the time. I just sort of write the two vectors above each other, and then I can sort of imagine visualizing I, J, and K up there and doing its thing. So you get I, lots of 0, 2, 2, minus 1. Take J, and you would cross off the ones underneath J. So 1, 2, 3, minus 1. Plus K, 1032. So you're going to get I, lots of 0 times minus 1 is 0, 2 times 2 is 4. J is minus 1, so that's 1 times minus 1. Take 2 times 3. Plus K, now 1 times 2, take 0. So this is minus 4I, take plus 7J, plus 2K. All right, so that's the cross product of A times C. We can write it as a nice vector. There it is. Now, next thing we'll need for this angle formula is sort of the modulus of the two vectors crossed together. So if we look at doing mod of A times C, that's going to be square root of minus 4 squared, 7 squared, and 2 squared. And we can work that out. So that's 16 plus 49 plus 4. So that is, let's see, 20 plus 49. All right. Mod A we need as well. So that's 102. So that's root 5. And mod C, 32 minus 1. So 9, 4 is 13, 14. Cool. All right. So now that we have all three of those pieces, mod A cross C equals mod A, mod C, sine of whatever the angle is between them. So root of 69 is root of 5, root 14, sine theta. We can get sine of theta is root of 69 over root 5, root 14. And then we just work out what that is. So it's going to be inverse sine. And we'll put all those square roots on. So about 83.135. Make sure your calculator's in degrees. If it's not, just set it to degrees in shift setup. 83.1. Cool. We should be able to get the same angle using the dot product. So if we use the dot product formula, A dot C is mod A mod C cos theta. So when we work out A dotted with C, that is 1 times 3 plus 0 times 2 plus 2 times minus 1. You just dot all the bits together. Root 5, root 14 cos theta. So that is going to be 3 take 2 equals root 5, root 14 cos theta. So that is 1 equals root 5, root 14 cos theta. And then we can just do cos of theta is 1 over root 5 with root 14. and we'll see what we get there. So if we go inverse cos of that, 1 on the top, root 5, root 14. Get the same angle, 83.1. So it's always good to do that. You can probably see the dot product method is a lot easier to use. So if you are just calculating the angle between vectors, I'd really encourage you to use this way. But it's important to know both, especially for like proofs and stuff as we get into the properties of cross products.